Good afternoon, everyone, and welcome. Also, good morning to somebody some of the folks joining in from the West Coast. All right, so today's topic is going to be bridging the gap and aligning, pressure results from simulation and the real world. I think pressure is the one of the key factors why a lot of the industry folks trust Moldex 3D when it comes to pressure prediction, and we have a good way of understanding if there are any discrepancies between the results, why it's happening, what's causing them. So that's what the topic is for today, and it's going to be a very short webinar, but it's going to be mostly focused on it's going to be mostly like a guideline to help you when you see discrepancies between the real pressure in the production world versus the simulation. I'm Harshal, so without further ado, let's begin. And so topics for today's, so we have divided into three sections. First, we're going to talk about what is sprue pressure. How simulation calculates it, and then what we're going to do is we're going to talk about evaluating pressure discrepancies in simulation if you see any between the production and simulation, and then we're going to talk about how to fix those discrepancies or what to look for when you run into this kind of situation, and try to troubleshoot on your own, right? So what is a sprue pressure? Basically, pressure reading inside the simulation is from the melt entrance. You can see it on the image on the right. Red is marked as a melt entrance. So that's where the pressure is recorded inside the simulation. So if you have anything above that, for example, like a nozzle geometry, or if there is a hot runner, we want to make sure that we place the melt entrance, at that and not on the cold runner. Because we want to, this is where the calculation will start from, and we want to consider the accurate starting point for it. Another important thing is making sure that the runner geometry is not generic, but is exactly matching the production, what we are trying to simulate. So we want to make sure that the geometry we are considering inside the simulation is exact match of what we have in the production, right? And then the filling stage is velocity controlled, and the pressure will need to increase to maintain a constant flow rate. So any resistance, what we are doing here is velocity is controlled. There might be resistance, and to overcome that resistance, the pressure might go up during the filling process. So that's what we do. And then everything after the melt entrance will begin to cause flow to restrict, right? As it is passing through the gate, through the different features inside the part. There will be a lot of restrictions. So what the pressure, we will see the rise in pressure, right? So restriction of the flow will cause the pressure requirement to increase gradually, so it will go up, right? So we can track those, and it will calculate that. Only objects after the melt entrance will cause the pressure drop. So all the models after the melt entrance will continue to cause the pressure drop and will be calculated. Anything above won't be. So all significant sources of pressure loss should be considered inside the simulation. Like I said, if you have a nozzle, hot runner, you have the design for it, please consider it. That will be important in capturing the accurate pressure and comparing between simulation and production.